Failing to prepare is preparing to fail. So as responsible Bitcoiners, we are making ourselves ready for the fight against quantum computers. And in doing so today, we are going to examine lattice-based cryptography. Post-quantum cryptography has a few algorithms within it. So they are further subdivided depending on the mathematical problem they are basing their security on. So in this regard, we have hash-based cryptography, code-based cryptography, multivariate polynomial-based cryptography, isogeny-based cryptography. From all these, hashes may look more familiar because in the Bitcoin code base, hashes are everywhere. But apart from all that, we have lattice-based cryptography that is very promising, and we are to see its fundamentals in an introduction today. We will try not to oversimplify things, but again, avoid any unnecessary complexities of the matter. So in our ferry flight towards understanding lattices, we are going to see a brief history of them, so we know where they start from, advantages and disadvantages, what are their security guarantees, a brief example of comparison between lattices versus hashes, so we know where they stand in the competition, and some cryptanalysis tools. Then, at cruising altitude, we are going to formally define lattices and their bases. We are going to see the Minkowski's theorems. What are the NP-hard problems that lattices are basing their security on? The Lattice breakthrough that made the practical lattice-based cryptography possible. The q-ary lattices, a very important cryptography context. The average case problems that are the real cases of lattice-based cryptography, and learning with errors public key encryption scheme with examples. At landing, we are going to relate back to Bitcoin and see what is the threat of quantum computers, what are the trade-offs that we are going to face, why we may choose or not choose lattices, and what stuff we can do. To further continue with the history, we can't avoid mentioning Pythagoras with his geometric number theory. If you remember, the triangular numbers and stuff like that are based on fragments of lattices. Then 3rd century AD, Diophantus was trying to find integer solutions in Diophantine equations. After 2 millennia, Lagrange took over at 1773 with introducing some lattice concepts again in his work in reduction algorithms for binary quadratic forms. And then the usual suspect, Gauss, in his work Disquisitiones Arithmeticae in 1801, he introduces concepts of lattices even more through his quadratic forms geometrical representation, the Gauss reduction, quadratic reciprocity law, and while representing integers are sums of squares. Now, 100 years later from that, Minkowski defined geometry of numbers, and he stated two very important theorems, the convex body theorem and the successive minima theorem, which are also known as the first and second Minkowski theorems. And he said, with these theorems, he set the dialectical mathematical foundation for modern lattice-based cryptography. Now, another 100 years later, we have the LLL-based reduction algorithm that is used in lattices, but its intended purpose is against factoring polynomials with rational coefficients. Now, the most important thing in this slide, 1996, Einstein published a paper generating hard instances of lattice problems, and with that he made the practical lattice-based cryptography possible. And after that, a cascade of development began with the introduction of the NTRU algorithm, which is the first practical lattice-based public key encryption scheme, and then the LWE by Regev, the ring LWE, module LWE, and the like. And we conclude that brief history with the NIST competition between 2016 and 2024, when they evaluated hundreds of post-quantum algorithms, and they ended up with 4 finalists that we're going to see on the next slide. So what are these finalists that are recommended for industry? These four algorithms are the ML. So one of them is for key encryption, for key as a key encapsulation mechanism, and the other three of them are for digital signatures. So MLCAN is based on Crystal Kyber and is a module lattice-based key encapsulation mechanism. It's intended as the primary standard for general encryption. Now, for digital signature, we have three algorithms. MLDSA, which is based on Crystal's dilithium, and again it is based on module lattice-based. SLH-DSA, which is based on the Sphinx Plus, and it's based on Staedtler hashes, and is intended as a backup method in case MLDSA proves vulnerable. And lastly, we have FNDSA, which is another version of digital signatures based on a fast Fourier transform over the NTRU, again based on lattices. What is the interesting, what I have noticed to be very interesting fact in this slide is that the 3 out of 4 NIST finalists are based on lattices, and the one that is not is based on hashes and is intended as a backup. So I think there is some merit to that, and we will find later if there are truly advantages with lattices. Now, let's move on some advantages of the lattices. Well, they have competitive efficiency and performance because they are using number theoretical transforms and fast Fourier transform for fast multiplication. They have great simplicity, and when we say great simplicity, we mean great simplicity on their mathematical structure. So they are just based on vectors and matrices, which is plain linear algebra, and some modular arithmetic on top of that. So nothing fancy in the mathematics, which is very, very nice for the underlying cryptography. They also have algebraic flexibility. What we mean by that? We can do operations between matrices and vectors, not random ones, but with a specific dimension, but still we can have operations between them. If you compare that with hashes, well, hashes do not have any algebraic flexibility, because if you hash something and you hash something else and you add them together, you will get a very different result of hashing the sum of those before. So hashes, no algebraic flexibility; lattices, great algebraic flexibility. So apart from that, they have cryptographic versatility as well, because they support a full range of cryptographic schemes like public key encryption, key encapsulation, digital signatures, and even full homomorphic encryption. They also support advanced features for the post-quantum era, like ZK proofs, multisig, and the like. And last but not least, they are based on NP hard problems. So all problems that we have seen up to now in our domain are NP or NP intermediate. But it's the first time that we're going to see NP hard problems, and this is a very great security advantage that lattices have. Now, another advantage of lattices is that there is a bold statement here. There is no polynomial time classic or quantum algorithm that approximates lattice problems to within polynomial factors. That means that quantum computers cannot break lattice cryptography. And this is because QFT, and QFT is the quantum Fourier transform that is used in the source algorithm, seems to not be applicable to lattice problems. And attempts to break lattices are since the source algorithm discovery in mid-1990s, so we have a full 30 years of cryptanalysis against lattices. Now, another great advantage of them is that their security guarantee. So, breaking the cryptographic construction implies an efficient algorithm for solving any instance of some underlying lattice problem. So, either you break lattices, all of them together, or you cannot just solve an instance of them. And this is a very distinguishing feature of lattices, and we can directly compare that with like RSA, where we are factoring semi-primes. To remind you, semi-primes is a number that is the multiplication of 2 primes. So this problem is hard on average, but there is no guarantee that it is hard for every case. For example, if you take 2 prime numbers that are close in range to one another, you can use Fermat factorization to very easily find the factor of this number. Not the case for lattices, because for lattices either you solve them all, or you cannot just simply solve one random case. That's a very distinguishing characteristic of them. And it's very counterintuitive, so we will look more on that. Now, everything comes with a disadvantage, so lattices cannot avoid that. One main disadvantage is that they have implementation complexity and side challenge that go hand in hand. And by side challenge, we mean that you can break their security by not attacking to the main security assumptions, but through like power monitoring or memory monitoring or stuff like that. So one problem is that as number theoretic transforms are built, they are using intermediate variables that are stored on the cache. So the processor has to go back and forth from the cache, and if somebody is monitoring these patterns, then maybe he can reveal some coefficients of the secret, which is really bad. And then there is another thing, that execution time shall not depend on the secret, because power analysis may reveal coefficients of S. And yes, it is very difficult to build functions work that way with lattices. But these problems can be solved, though difficultly. Another disadvantage of lattices are their security estimation challenges. So their security that do not scale smoothly with lattice sizes. So for example, if you have AES 128, it is less secure than AES 256, that's straightforward. But in lattices, this is not the case. You may have two algorithms with 512 size of matrices, and they will probably have very different security depending on other parameters. This is why the next bullet says that parameter selection challenges are also difficult. But we will see what these parameters are and how to select them. And the last disadvantage that I could find is that they are less battle tested. However, on their credit, they have been through exhaustive cryptanalysis for the last 30 or so years. Now, let's do a brief comparison between two algorithms, one hash-based and one lattice-based. Both of these algorithms will be from the post-quantum category, so we will be directly comparing similar things. So on the green column is the MLDSA, which is lattice-based, and on the orange column will be SLHDSA, which is hash-based. And let's check these categories one by one. So in the security assumption, lattices are based on NP hardness of lattice problems. They have strong theory. On the other side, hashes are based on collision resistance, which is heuristic. We have average case security, not worst case security. So apart from that, in practice, they are very strong. So depending on if you are a man of theory or of practice, you will have a preference here. Strong theory for lattices, strong practice for the hashes. Now, for the security proof, it follows that lattice-based have worst case to average case reductions, which is again formal proof, a formal mathematical proof. For the hashes, we just make sure that we end up basing our security only on hashes. So, very strong formal proofs for the lattices. Now, what about the key sizes that we are very interested in Bitcoin? Because we want to keep sizes small to fit in a block. Lattice-based have key sizes of 1.3 kilobyte. It's kilobyte, which if we compare to hashes that they just have 32 bytes is an extreme difference. So very small key sizes for hashes, medium size for, because these kilobytes are considered to be medium size for lattices, but again, very big distance. However, lattices are more compact in their signatures, because if you combine key sizes and signatures, lattice win, because on signature sizes, lattices have like 2.4 kilobytes, but then hash-based goes up to 8 kilobytes. So if you combine 1.3 and 2.4 is far, far less than, well, 8 kilobytes. So lattices are more compact, but they have some bigger keys. So what do we have on speed? It turns out that lattice-based algorithms are very, very, very fast, and they are even competitive with elliptic curve cryptography. while on the other hand hashes are really slow, and especially during the signing procedure. And if you trust NIST for the matter, they designate lattice-based cryptography to be their primary choice, while hashes are intended as a backup. However, I have to say here that Bitcoin relies its security on hashes, so here hashes do not change the security assumption for Bitcoin. But again, maybe this is a matter of preference. Let's move on now. What are some cryptanalysis tools that we can use to evaluate lattice-based cryptography? Well, the first one is the LLL algorithm, invented in 1982, but it can evaluate lattices, but it doesn't break good lattice algorithms, because it has exponential running time to break the hard problems, and also the space requirement that it needs is also exponential. However, it is surprisingly useful in factoring polynomials over rationals, like the RSA. Next, we have the BKZ algorithm, that is just an LLL generalization with the more tunable parameters. Again, exponential running and space requirements, they cannot break lattice-based cryptography, just evaluate it. So, up to this point, we have seen an introduction of lattice-based cryptography, what's their history, their advantages and disadvantages, where they stand into the competition. But enough with the pleasantries, because now we're going to look on some formal mathematical definitions of the concept. And as John von Neumann said, in mathematics, you do not understand things, you just get used to them. So don't be worried too much, because we will use mathematics just to explain the concepts, and concepts is what we care about at this point. So let's look on this slide. So on the left part of the slide, we see that what is a lattice? A lattice is a set of points in space with a periodic structure. This is a two-dimensional lattice. You see there's a periodic structure of them. So the first thing we notice is that there is dimension for the lattice. Here in our example, it is two dimensions. Well, one dimension in X and one dimension in Y. But we can have lattices with 2, 3, 5, 40, or even thousands of dimensions. Now that we know what the dimension of the lattice is, we will define the basis of the lattice. So if you see these vectors, they may form a base of this lattice. The number of them will be equal to the size of the dimension. So if we have two-dimensional lattice, we will have two basis vectors. If we have 10-dimensional lattice, we will have 10 of them, 10 basis vectors. So these vectors are linearly independent between them. So the projection of the one is 0 on the other. Now, if we have the basis vectors, we can define the basis of the lattice. The basis of the lattice is a matrix that each column of this lattice is a basis vector. You can see the definition here. So B1, B2 up to Bn are the vectors, and B is the basis matrix. So just a quick note on the formalities. If you see a capital letter that is bold, this is a matrix. If you see a lowercase letter that is bold, it is a vector. If you see a normal letter, it is just a scalar. So now that we know what the basis of the lattice is, we can define a lattice, because the lattice is nothing else but all linear combinations of the base vectors over the integers. If you look at this definition over here, the lattice lambda, the Greek lambda we use for the lattices, so the lattice lambda with the base matrix B is all the linear combinations between the base matrix B and X, where X is a vector of the same space, of the n space. So we take random vectors, multiply them with the basis matrix, and then we get the lattice points. But remember that the vector X must have only integer coordinates. And this is throughout our discussion, lattices and are concerned with integer values, nothing else. The last thing I want you to see in this slide is that delta over here if you see this rectangle, this one is called the fundamental parallelepiped. I will not say that name again. I will just say that's the fundamental cell, and we will be concerned about the area of this fundamental cell. We will see that on the next slide. So let's move on with some more definitions that we are going to use later. The determinant of the lattice. What is the determinant of a lattice? Basically, we go back to the previous slide. The determinant of the lattice is the area of that fundamental cell. If this is an area because this is a 2D lattice. If it was a many D lattice, this would be a volume, etc., etc. And you can see that the smaller is the determinant, this area, that means the more dense is the lattice. If that area was big, that means that the lattice would be very sparse, meaning that the points of the lattice would be far away between one another. So we know from linear algebra how to take the determinant of a matrix. So if we take the absolute value of the determinant of the basis matrix, we get the determinant of the lattice. And you notice here that it will always be a positive value, and this is true because it will be an area. We will not have a negative area. With that, as we can define a unimodal matrix, we can define the unimodal lattice, which just means that its determinant is equal to 1. So if we have a basis matrix that the determinant is 1, then the determinant of the corresponding lattice will be 1. And this, because 1 is the smallest integer here, this means that a unimodal lattice has the maximum density, because the lattice points will be close to one another. And just because we have unimodal lattices, and these are not unique, we can have many of them, many lattices with the determinant being equal to 1. From that it follows that we can have a lattice can have multiple bases. So you see here there exists a U, so the lattice with basis B will be equal to the lattice with basis B times U, which is another basis B prime. A very important concept now is the dual of a lattice, which is nothing else than the set of all vectors y whose inner product with every lattice vector x is an integer. So we are multiplying vectors y with vectors x. X is a lattice point, so the corresponding vector of a lattice point x is the vector that goes from the origin of the lattice to that point x. So to see that mathematically, lambda star, which is the dual of a lattice, is all the vectors y, okay, that if we multiply y with the lattice points x, we get an integer. So if this condition holds, vector y is a member of the dual lattice. A very interesting property of this dual of a lattice is that the determinant of the lattice is the inverse of the determinant of the dual of the lattice. This is important. Now that we know these definitions, we can see what is the cryptographic property of lattices. What is that property that we need to have secure algorithms based on lattices? Well, lattice cryptography is based on the fact that a given lattice can have widely different bases. As we saw previously, not only one base, but a lattice can have many bases. So on this property we will exploit to build secure systems with lattices, because the security assumption is that it is computationally infeasible to recover a good basis from a bad one. So we can have good and bad bases, and this is what we are going to look at now. What is a good base of a lattice? Well, if you see here the figure, this is the base of that lattice, and you notice that it has short base vectors. They are nearly orthogonal between them, and if you have this kind of base, you can do any computation you want on the lattice pretty easily. So it simplifies the computational tasks significantly, these kind of bases. And this is why it is used as a private key. Now, we can also have very bad bases on lattice. If you see here the figure, these are very long bases. They are highly skewed, which means they are almost parallel to one another. And this makes computational tasks impossible, almost impossible in the lattice, because these two vectors are very big and with a small angle between them. And a possible attacker cannot recover short vectors from these kinds of bases. And this is why these vectors, this bad base, is used as a public key. Now, what are the NP-hard foundational problems that we have the lattices basing their security on? So we know. Two of them are listed here. So the first one is the SVP, or shortest vector problem. What is the problem here? The problem statement is find the shortest non-zero vector on the lattice. This is a homogeneous problem because everything is on a lattice. We are looking for vectors that are on the lattice and we want to find the shortest of them. There are approximation variations of this problem. If you see here with the subscript gamma, SVP gamma. Gamma is just a factor and denotes how many times bigger a base we try to find than the short vector. So we don't want to find just a short vector because it might be too difficult. We want to find gamma times the small vector, 3, 4, 5 times the small vector. So it is easier for us. There is a corresponding problem called the closest vector problem, and the problem statement here is find the vector closest to a given target point. So we have a lattice spread, and then we have a target point. This target point doesn't necessarily need to be on the lattice. Probably it's not on the lattice. And we want to find a vector in the lattice that passes closer to this target point. And just because this target point is not a lattice point, it is called an inhomogeneous lattice problem. So these are the two NP-hard foundational problems that lattices are basing their security on. These are theoretical and not practical, and we will see how we will get practical problems after them. But now, let's inject some adrenaline into your bloodstream, so maybe you wake up a little with a quiz. And let us find a short vector on the following 2D lattice so we can see how difficult or not it is to solve these NP-hard foundational lattice problems. And again, just remember that we are interested in big dimensions, because maybe in dimensions like 2, 3, or up to 40, these problems can be solved. But if we are talking about 500 and more dimensions, these problems are provably hard to solve. So let's see here. We have a lattice on the left. We have these two basis vectors, B1 at coordinates 8, 3, B2 at coordinates 5, 7, and these two define the lattice. We don't need to see all the lattice, we just need to see all just these two vectors, because any integer combination of them will give us a point in the lattice. So what we need to do now is to find a short vector. We have these two vectors and we need to find a short vector from them. So basically we need to solve this equation. S, this will be our short vector, will be equal n times the B1 plus n times B2. So how we are going to solve this problem? What is a short vector? So one way is to think that maybe B1 is a short vector, or maybe B2 is a short vector, who knows? Let's see. So let's calculate B1 and B2 to see what their Euclidean lengths are. So we take this norm from the Pythagorean triangles and we solve for B1. The length of B1 will be 8.54 and the length of B2 will be 8.6. But again, are those short vectors? We're going to see next. But in the meantime, can we find a vector between those two that has a smaller length? Well, one solution is to use small numbers or on n and m and try to find if they produce a vector whose length is shorter than B1 or B2. And the easiest thing to do is just subtract the two vectors. So if we set n to be plus 1 and m to be minus 1, effectively subtracting B1 from B2, okay, we subtract their coordinates and we find the vector s, our short vector, supposedly, to have the coordinates 3, minus 4. And if we take the Euclidean norm of it, it will be 5. So, yes, we found a vector that has shorter length than B1 and B2. But again, is this a short vector? So, hopefully we have Minkowski's theorem that tells us if a vector on a lattice is short or not. So, This is the first theorem of Minkowski, and gives us the short vector existence. The general statement of this theorem is that we're going to read it and explain it later. So any convex region R, symmetrical about the origin of the lattice, of volume greater than 2 to the n, where n is the dimension of the lattice, includes points of the lattice other than the origin. So in order to understand this, let's take the case that the dimension is 2. So we are just talking about the two-dimensional space. A convex region in two-dimensional space could be just a circle. And the dimension is 2, so 2 to the n is 4. So we can restate this problem and say any circle, symmetrical about the origin of course, of volume greater than 2 to the 2, which is 4, includes points of the lattice other than 0. And this sounds simple because, okay, if you expand a circle, it will definitely include some other lattice points, but here we have a bound. So from that, a corollary is that that point defines a short vector, and the maximum length of this short vector is less or equal to the square root of the dimensions times the nth root of the determinant of the lattice. So this is a very important theorem, because it gives us the existence of short vectors and how big they can be. This way we can evaluate if we find short vectors, if we find lengths of vectors, we can evaluate if they are short or not. But not only that, we have Minkowski's second theorem as well, which is the successive minima. And this says that the product of the first few successive minima is also bounded, and it guarantees not just one short vector, but several. So this might seem a little bit tricky, but if these are the short vectors, and we will have as many of them as the dimensions are. So let's go back to our two-dimensional problem. It will be just lambda1 times lambda2 will be less or equal than 2 to the 2, which is 4, times the determinant of L over the volume of the convex body, the volume of the circle, which is the area of the circle, and we normalize that, so we don't care about it that much. We will see in the example. Some remarks here that we have this equation. If we make the determinant of lambda huge, which is on the numerator, you see that it is probably that short vectors are probably hard to find. This is the foundation of worst case to average case reductions, and it's used in security proofs of learning with errors, ring learning with errors, and model learning with errors. Now let's go back to the example and see how these theorems are applied to find our short vectors or not. Firstly, we will compute the determinant of the lattice, because we will use it in these two theorems. The determinant of the lattice will be the absolute value of the determinant of the basis matrix, and you notice here this is the basis matrix, because 8, 3 is in this column is the vector B1, 5, 7 is the vector B2, so this is the basis matrix, and we take the determinant of that, which is 41. Now, on the left here is the first theorem of Minkowski, and we find that lambda1, if we substitute that determinant here and set 2 to be the dimension of the lattice, we see that the lambda1, the short vector can't be lengthier than 9.06. Now, because we are in two dimensions again, we will have two successive minima, so lambda1 times lambda2, here is the formula that we just substitute the values, and it has to be less than 1.164. So with these two bounds, we are going to check what we had with our vectors. Here we computed the length of S to be 5, and then for B1 and for B2 we had 8.54 and 8.6 as their lengths. So we notice that all of them actually are less than 9.06. And then we will just use, because we will be needing two successive minima, we will use lambda1, the 5, and from these two, the smaller one, why not, lambda2, which is 8.54. And now we will see if they fit in the second theorem of Minkowski. Excuse me. So if we multiply these two values, we get a 42.7, which is far less than 164. So yes, we found two short vectors, actually three, But again, in 2 dimensions, this seems to be easy. But when we go more than 4 dimensions, this is impossible to do. One more thing that we may talk about at this point is that lattices don't need to be orthogonal. Okay, don't need to be squares. So it can be skews, as we see here in our figure. They can have an angle here other than 90 degrees, and this is easily provable because this would be the area of the fundamental cell, and it will be equal both to the determinant of the lattice and to the trigonometric function that we are going to use to find that area. And if you solve for that angle theta, you can easily find that it is like 34 degrees, and you can convince yourself that lattices do not need to be orthogonal. They can have actually any angle between their basis vectors. But that's just a corollary of all that stuff. Now let's move on to a more conceptual thing again. As we said in the introduction, Einstein had a breakthrough that made lattice-based cryptography possible, and this is because average case problems are at least as hard as NP hard foundational problems. This is completely counterintuitive, but again, I will say it again because it's too important. Average case problems are at least as hard as NP hard foundational problems. Up to now, we have seen what are the NP hard foundational problems. We have seen SVP and CVP. We haven't seen what are the average case problems, and we will do so after we examine what are the q-ary lattices. Now, as I just said, we need the q-ary lattices to define the average case problems. So this is why they are very important, and we will take the trouble to do them. But as it seems so, they did not came out of the blue. They are based on coding theory, and in coding theory, we are concerned with two things. We need some way for the sender to generate the codes, send these codes over a noisy medium to a receiver, and then the receiver needs to know that the data that they got are the correct ones. So we have two kinds of matrices in these linear codes from coding theory. We have the generator matrix that generates the codes, and we have the parity check matrix, the matrix that checks if the codes are correct. So based on this concept and this concept alone, we are going to define these q-ary lattices. So we are given a matrix A of the dimensions m and n, m by n, which is an integer mod q. Okay, we cannot avoid that. And with that, we define two q-ary lattices. The primal q-ary lattice, see that subscript q means that it's a q-ary lattice with the basis of A, which contains all vectors that can be written as integer linear combinations of the rows of A mod q. And this relates to the concept that we just said, the generator matrix. If we see this equation, we can see that again. The primal q-ary lattice contains all the vectors of this dimension that they have this constraint that they are linear combination between the matrix A and vectors S. And these vectors S, of course, are integers, mod q. And this is the primal lattice. The dual q-ary lattice contains all vectors that are orthogonal to every row of A mod q. And this would be the parity check matrix that we just said. To see the formal definition, it will be the q-ary lattice, the dual q-ary lattice will contain all vectors Y that if we multiply these vectors with the matrix A, we will get a 0. This would be our parity check. So now that we have defined these q-ary lattices, it follows that these duals are scaled duals of each other. This is a funny property here, but it is only possible because of the modulus operation. So the one is q times the dual of the other, and the other is q times the dual of the one. Most interestingly, they both have determinants approximately equal to q to the n. What is q to the n? So q is the modulus, n is the dimension, and in practice we will be using like a q of a few thousands, like 4,000 something, probably a prime number, and then n will be the dimension, which is like 512. So this determinant will be huge, and just remember that the determinant has to be big. So this way the q-ary lattices will have big determinants. Now, we will examine this group equation here. So, if we see the right part of that, the lattice is a subgroup of the vectors, of the integer vectors. So we can say that all vectors in the lattice have integer coordinates. This is a very important thing. Again, we are talking only about integers. Lattices, integer coordinates, full stop. Now, on the left part of this group equation, every vector whose coordinates are multiples of q, say q and an integer, is in the lattice. And this gives us a quick check to see if a vector is a member of the lattice. So we just need to, if we want to check the membership of a vector, we do. This is determined by y mod q. So if y mod q checks out, then this y is a member of the lattice. That meaning that the coefficients of the vector y are multiples of q. Now, this is a rare case, of course, for a vector to be in the lattice, and we have two subdivisions here. So if that vector, apart from checking out with y mod q, has the property that is a linear combination of the basis matrix A times, so meaning it's all the linear combinations of the matrix A, then it will be a member of the primal lattice. In another case, if it satisfies the property A times y being 0, then it will be a member of the dual lattice. So there will be thousands of other bullets here, so these are the minorities, and this is why it will be difficult to find the short vectors. But this is how we check the membership of vectors being in the lattice and then being in the q-ary lattice, the primal or the dual, like a check. So, some remarks here. We keep q small, and q will be usually a small prime, not a huge number in RSA. And for two reasons. We are interested in q being far less than the determinant in order to control the number of short vectors. So if we have big determinants and we have small q, it will be very difficult. We will have a small number of short vectors, and it will be difficult to find them. And we like to keep it that way, so the attacker cannot find these short vectors, but it has to be sufficient so we can recover them as well. And q being small enables fast modular arithmetic because we reduce mod q in every step. So if q is small, we have to deal with very small numbers, and operations will be really fast. And last but not least, q-ary lattices allow average case hardness assumptions that reduce to worst case lattice problems, as we have said again and again. Now, what are these average case problems? Because we took all the trouble to define the q-ary lattices, now we are able to define the average case problems. The first of them is LWE, or learning with errors. And what it is, it's distinguishing noisy points near the primal lattice from uniform random points on average. We will see figures explaining that, so don't worry too much about it, but a very interesting thing is that it is as hard as worst case approximate SVP. Improvements of this problem comes with structured lattices that enable number theoretic transforms. So in modern algorithms, we will have a ring LWE and module LWE, not just the theoretical plain LWE that we are going to see. But it will be for our educational benefit to examine the plain LWE errors. Another average case problem is the SIS, or short vector integer solution. Here we are just trying to find short vectors in the dual lattice on average. On average means at random. And again, it is as hard as the worst case approximate SVP. We just mentioned here ring LWE and module LWE. We will not get into the trouble in this talk to define them, but I have included modules and rings on an appendix here later on the lecture. So if you want to see by yourself at your own time, you can just quickly see the definitions of modules and rings. But now we are going to examine more the learning with error problem, and we said it will be how to distinguish noisy points near the primal lattice from uniform random points on average, which is basically how can we solve this equation. We have a matrix A, n by n, a secret S, a vector n by 1. Here will be, this will be the error, the induced error, or the noise, if you prefer. This will be m by 1, so the dimensions match, and then this will be equal to b, which will be a vector m by 1. So then what we are given here will be a and b, and in the presence of this noise, we have to find s, which it turns out to not be possible for the attacker. So to further illustrate this problem, I mean, if you didn't have the noise, S would be very easy to find. It would be like A times S equal to B, one unknown, two knowns, S would be very easy to calculate. But with the presence of the noise, things are getting complicated. And let's see the next slide. So here will be the secret space where S vectors live, okay? And here will be the B, the solution of the equation A times S plus E. So here will be the points. Here will be the points that correspond to S, but the E creates an error bubble around them. So let's say an attacker is given this point here that the cursor shows. How on earth will he know if this belongs to an error bubble or it is outside of the lattice? For this to work, these bubbles have to be independent from one another. They have not to overlap with each other. And to secure this, we have to set that the dimension m has to be far greater than the dimension n in order for the bubbles not to overlap. So you can go from the secret to the solution of this equation, but you cannot solve this equation and go back to the secret. And this is the security of the learning with errors problem, which is as secure as the NP-hard foundational problem of the SVP. And to see the formal definition of the problem, now that we know what is going on, the learning with error problems that has these four parameters, m and n, these are the dimensions of the basis matrix, q, the modulus that we are going to take, and b, a small variable that we are going to just define. So let S be our secret that is randomly chosen from a vector space of integers mod q with dimension n. So S will be a vector with dimensions n modulo q, and this will be our secret. We will choose an error, which is again going to be a vector but with dimension m, and all the coefficients of this vector has to be between the variables minus b capital and b capital. This is just a number, and the small number that we choose to be far less than q over 2. So now, given the matrix A, which is again randomly chosen between the space m by n with integers mod q, and the solution of this equation, which is b, okay, then try to find S. This is exactly what we have been visually defining before, but just to have the formal definition of the problem here. Now, we are going to examine how a crypto system based on learning with errors works. So the first thing we are going to examine is how the key generation takes place. What are the equations for the key generation? So here will be our secret. We just said how we are going to sample it. Here is the matrix A, and here is the error or the noise, as you prefer, E. We compute B to be A times S plus E mod Q. So we know we get A randomly, we choose our secret randomly, we choose the error within these bounds randomly, and then after doing so, we set our public key to be the matrix A and the solution of this equation B. Okay, so this will be a matrix and a vector, and we keep for ourselves the primary key to be that secret vector S. So we have generated our keys, both the public key and the primary key, under this structure. Now, how we are going to go about encrypting a single bit? We have the public and the private key, but how can somebody encrypt a bit and send it to us? So let's say that this bit is mu, which can be either 0 or 1, because we are in the digital world. and he will choose a random vector r, and this vector will be of dimension m, and it will have coefficients either 0 or 1. So it will be a vector like 0, 1, 1, 0, 1 with random values of 0, 0, 1. Then he will compute these two equations. V will be congruent to the vector b times the vector r. This will be an inner product. Plus, this is a scalar, mu, which will be either 0 or 1, and the floor of q over 2. We take the floor of q over 2 because q will be a prime number, so if you divide a prime number over 2, it will not be an integer, because prime numbers, except from 2, that we are never going to use, are odd numbers. So this will be this has to be an integer, and it will be multiplied by either 0 or 1. So again, all this will be an integer. Again, working with lattices implies integers. And we'll take the modulus q of that, and we then compute u congruent to the transpose of our matrix A times the random vector R mod Q. And when we do these two computations, we set our ciphertext to be the tuple of V and U. And again, V will be just a number, U will be a vector. So this will be the encryption process. And how will we decrypt that single bit that we have been sent? So the decryption equation is this one. This W is an intermediate variable, so this is not the solution. We will branch on this solution to find the decryption, but this is an intermediate computation, so W will be equal. We will compute W to be equal to the scalar part of the ciphertext minus the secret times the vector part of the ciphertext. And again, this is an inner product, so it will be a scalar. W will be a scalar, just a number. And of course, we reduce mod Q. Now, we will branch on whether this intermediate variable, the absolute value of this intermediate variable is less than Q over 4, mod Q. If it is so, then our message is 0. Otherwise, it will be 1. And notice that the rounding can tolerate the error, and we will see why. So, again, we are talking about W. W is our intermediate variable. So we have calculated, in this slide, we have calculated, let's say that we have calculated this W, and now we want to check what is mu, because this is further complicated. Let's unpack this. So, we have W, and then we go to our Q modulus to see where this W fits in. So, if it is between the ceiling of minus Q over 4 up to the floor of Q over 4, again, because this has to be an integer, this will not be an integer and is not included in our modulus space. So if it is between minus Q over 4 ceiling and the floor of Q over 4, then our message will be 0. Now, if W is from the ceiling of Q4 larger than the ceiling, bigger than the ceiling of the Q over 4, and less than the floor of minus Q over 4, okay, and again, we are in a modular space, so then we will assign it to the value of 1. So this is how we get our intermediate variable translate into the message being 0 or 1. And if you are interested to see if this, how this works, we can have a look at the sketch of the proof, of the decryption proof. So let's see here why this decryption works. It's very interesting. We will begin with the decryption equation and the ciphertext. Because if we see here, for the decryption, we just need the ciphertext, which is V and U, the tuple of V and U, the secret that we already have, and then unpacking the ciphertext, it will be V equal to this part and U equal to the other part. The only thing we need to do here is compute that BR, that inner product, and let's see how we do that. We start from the key generation equation. So if you remember, this B congruent to AS plus E is the decryption, the key generation equation. We take the transpose of both parts, and we multiply them by R here. So we have to take into account the transpose identities, which are a little bit counterintuitive, especially if x times y transpose is y transpose times x transpose. So if we do these computations, we end up in this equation. And look what we're going to do now. We will substitute this equation to the scalar part of the ciphertext here, and we will substitute the ciphertext into the decryption equation to get W. And if we do all these computations, we will end up in this equation. So it doesn't mean anything up to now, but we are now going to examine this equation. But remember how we got here for the intermediate variable to get what mu is. So we just saw that W is the inner product of ER. And what is the inner product? Now we know from linear algebra again that it will be the multiplication of all the coefficients of V with all the coefficients of R, and this will give us a scalar. But because R is either said to be 0 or 1, every Ri will be either 0 or 1, that inner product will only be the sum of errors in the points that the variable I dictates that the random coefficient of I is equal to 1. So we know by definition that the errors are less or equal to the small value b, and in the worst case that all of the coefficients of the random vector r are equal to 1, then it follows that the absolute value of our inner product will have to be less or equal to m times the variable b, which we choose so to be q over 4. So this is not a proof. This we choose this inner product to be less than, we choose r, so that inner product will eventually be less or equal than q over 4, and we will see that more on an example. And to continue with our decryption proof, now that we know what happens with that inner product, we branch with if nu is 0, then all this part will be 0, and w will be just equal to the inner product. But we just saw that in this inner product is said to be less than q over 4. And because w ends up to be less than q over 4, our decrypted message will be 0. In the case that mu is 1, so the equation here becomes like the inner product plus the floor of q over 2, then it is equivalent that w will be just the shift of mu by a factor of q over 2, and this thing will be again less than q over 4. And as we saw, it will fall under the south hemisphere over there, and the mu prime will be 1. So this was the sketch of the decryption proof. Very interesting, but maybe someone needs some time to work it by himself, but that's the sketch anyway. So now that we took the decryption proof out of the way and we know how our crypto system functions, we can see an example. So here is our toy example, and basically examples here are very important in order to understand the structure, the data structures involved, what is a matrix, what is a vector, what is a scalar. So I think it's really interesting to see and very easy to follow. So we set these 4 variables, m and n, to be the size of basically the matrix A. So it will be n columns by m rows. So we will have q as our modulus, the prime number 17, and then b, the small variable, will be equal to 2, and we have to check that 2 is less than 17 over 2, the floor of that, which it is, because 2 is far shorter than half of that. Then we will get the secret S for ourselves, which will be this vector. Again, we have just seen the matrix A, which will be m rows by n columns, and then the noise or the error vector, which will be this, and its values will be randomly chosen between -2 and 2. Okay, so this is our setup, our data structure setup. So we want to do the key generation now. Remember, we have this key generation equation here, So if we substitute everything that we have just said here, the matrix A, we multiply that with our secret, and we will add the noise E, the error E, and if we do the computations, we will end up with this vector for B. Again, you notice we have been reducing every step mod 17, so we don't do with the big numbers. So now we know B. And to recap, our keys here will be, for the public key, it will be the matrix A here, and the vector B, which is the result of the key generation equation, AS plus E. And then for the primary key, it will be just our vector S. So these are the keys. And if we want to encrypt something, first we have to check that the inner product of the error times the random variable that we are going to choose will be less or equal than q/4. So we choose a random vector r with ones and zeros as its coordinates, and we multiply e and r, and we found that it is 2, which is less or equal to q/4, which is 4.25, the floor of that. And now we can proceed because we find a suitable random vector. So to compute the first part of our ciphertext, which is v, remember v is a scalar, so v will be b, this is the vector b, this is the vector r, and because the mass as mu will be 1, here we set 1 for mu, and then q/2 floor, it is 17/2 floor, which will be 8, and then we get for v just the number 15 mod 17. So just the 15 for our v. This is the first part of our ciphertext. Now to compute the other part of the ciphertext, which is a vector, we multiply the matrix A, okay, the transpose of that of course, times the vector R, and we get this smaller vector 5, 14, 14, which is mod 17 for u. So now we have the ciphertext to be v and u with these values. And how to decrypt it? We want to compute again the intermediate variable w, which is the combination of our secret key with the ciphertext, with this equation over here. So if we substitute everything here, see v is the scalar 15, s is the transpose, s transpose is our secret vector here, and u, we just compute u here, and we get the value of 10. So w is equal to 10. Now, from 10, we have to decrypt them. We have to reduce it to what our message is. So we put 10 in that circle, and we notice that 10 is over here, so it is in the green area, and then it will get the value of 1. So this was our decryption. So let's relate back to Bitcoin. So as I said in the beginning, failing to prepare is preparing to fail, because the quantum threat is real. The SOR algorithm breaks ECDSA and the SNOR algorithms that are heavily used in our crypto system. There is that harvest now, decrypt later attacks, the long range attacks. Okay, we have the short range attacks, but the long range attacks are already here for any attacker to collect the data from the blockchain, because everything is visible. And the downside is that the Bitcoin's upgrade cycles are so slow. So we need to prepare early in order to be safe in the future. Now, what are the trade-offs between these types of new cryptographical systems versus the ones of the elliptic curves that we use? So the trade-offs are basically that they have larger sizes than ECDSA, which implies slower verification times and things like that, and there is no background compatibility. So this is why you see all these hybrid solutions coming on. We need a systematic solutions for that, because the cryptographic algorithms are not backward compatible. So systemic ways need to be found. But while lattices may come to the rescue because they have provable security from worst case that we don't have up to now, they are mature NIST candidates, if that means anything to anyone, and they will support PQ, multisig, governance, and privacy natively. And what stuff we can do? Of course, experiment further with lithium, Kyber, all of these new algorithms that NIST provided, contribute to research on developing Bitcoin, and why not help with quantum resistant soft forks whenever they appear. with that, these are some sources that I have used to prepare this presentation for you, and this concludes the presentation. You can find the full slide deck on my GitHub account. Thank you very much for watching that far into the presentation. Everyone, take care.